Hope you guys are feeling refueled and ready to go. So let's get started with setting up our development environments. For starters, we can go to the Build-A-Bot repo on GitHub. The link is up on screen there. There's a branch for each step under the 2023 namespace. So step 1 will be 2023/step1, and then /step2, etc. The repo is a guide. You can use it however you want. You can copy and paste, but I would advise trying to at least follow along and make it your own. Some of the snippets in the slide are slightly different from what's on the repository. I had to kind of remove comments and line breaks just to make it fit all nicely on a slide. If there are errors that you notice in my code, either on the repo or on the slide, feel free to tell me, but I will ask you to explain why, and I will ask you to explain how to fix it. So be prepared for that. And if you get stuck using Git, or if you've never used Git before, reach out to one of our helpers. Anyone who's wearing one of these black shirts with the Entelect Challenge logo, you can assume is a helper. So feel free to ask them if you get stuck. So for our bot, we are using Visual Studio 2022. You can use whatever you want. You can use Python, you can use C++, anything you want. This is just what we used because that's what we're most familiar with. So if you want to follow along with us, that's what we're using now. I think you guys did get an email on how to set up Visual Studio. I'm not sure. But Community Edition is fine. You don't need to shell out for a license. And in our case, if you go to the Visual Studio installer, we are using the .NET desktop development workflow. That's one of the main options you can select from the beginning. I'll pause here for a little bit in case anyone needs to catch up and install this stuff. OK, cool. We can move on then. So just to go over a brief introduction to SignalR, since we make quite extensive use of it in our game engine. It's an asynchronous event-driven messaging protocol. So what that basically means is you connect to our server or the runner hub, and then either the runner hub or your bot can send messages back and forth, and either end can listen for those messages and respond to them. And the message will be with a name. For example, we have receive bot state and send player command, and it can have a payload. Doesn't have to, but it can. So we are going to start our project. We basically open Visual Studio 2022, click the Create New Project button. So we selected C# from the language dropdown, and from the project type dropdown, we selected a console app. Then select the name and a path. We opted to have the solution and project in the same directory. But if you foresee yourself having multiple projects within your solution, feel free to leave that out. Then we're using .NET 6, but anything is fine. Maybe not .NET 4, but cool. OK, I hope most of you have gotten your project set up. If not, don't worry. There will be a break fairly soon for you to catch up and ask us for help. So I'm just going to cover a little bit about the structure before we begin in earnest. So basically, I'll present each step. Step 1, there's 4 steps in total, each kind of advancing on the bot a bit. And I'll make a point to explain what I did and why it was done. You can feel free to listen or code along if you think you can follow. And then after each step, there'll be 10 or so minutes afterwards just to catch up and ask for help or advice. At the end of each step, that'll kind of be your cue to switch branches on the GitHub repo if you are using it for help. And then after that, we'll proceed on to the next step. So for our first step, we're basically just going to start with adding some packages. So if you go to, if you right click on your project and select Manage NuGet Packages for Solution, you should be brought to a screen that looks a little bit like this. Make sure you select the Browse tab at the top. And then in that little search bar up there, you can search for the name of the package that we're looking for. And then you click the little checkbox next to the project name. By default, for me, it wasn't checked. But then once I checked it, it just stayed checked the rest of the time. So You can just leave it at the default versions, but the versions of the packages I will be using will be on the next slide. And then you just click install. These are the packages we are using for the bot. We have Signal R client, which is obvious that it is to connect to Signal R for the runner hub. And then the configuration and configuration JSON packages are just to read from a JSON file to configure basic settings about our bot. So I will give you guys some time to get those if you haven't already. Not long, we'll take a couple minutes. Okay, and we're going to move on now. So to start off with, we add a new app settings.json file to our project. And we right click and click on properties, and we make sure to set the copy to output directory mode to copy always. If we don't do that, when we compile our app and run it from the compiled file, it won't have the app settings file in its folder. So it'll give an error because it can't find it. Then these are basically just the contents of the app settings file. We basically just have the runner IP, which is the host to connect to. If you are running your the game engine locally, which I do recommend doing for local development, you basically can just set it to localhost. Then we have the runner port, which is set to 5000, and the bot nickname, you can name it whatever you want. It's your bot, you choose that. Then in our program.cs file, we basically delete whatever else is inside. We create a new class with a configuration variable, as well as a main function. We then set up a configuration builder and add the app settings.json to it as non-optional. So we make sure that it is required. And then we use the build method to read the configuration into our variable there. Okay, next up, we are basically going to read the environment variable from, or read the IP address from an environment variable. The reason we do this is because that will be determined when you submit by our cloud infrastructure, and it will set it in the runner underscore IPv4 environment variable. Keynote, make sure that you check if it already starts with HTTP before you append HTTP to the string. We've had in the past, some people have just blindly appended HTTP to the beginning, and then we basically just end up with HTTP, HTTP, and then the IP, and then your bot won't run when you submit it. The other thing is we read the nickname from the environment variable as well. For both the IP and the environment and the nickname, we read from the environment variable, otherwise we default to what's in the config. This is so that you don't need to set up too many environment variables on your machine, but then it should still work fine when you run it, when you submit it with us. Then, very important, you need to get the token from the environment. That'll be when you submit it. I will show you how to add it to your run and debug properties in Visual Studio. The token being missing is kind of why Tournament 1 broke, for those of you that were trying to submit. We will be back with it shortly, don't worry. But this is very important. You need that token. Then for the port, it's always run on 5000. We just left it at the default. There wasn't really much reason to change it. So that we don't need to worry about environment variables. We don't ever change it to something else. Then finally, we just assemble a little URL with the IP address, the port, and the /runnerhub endpoint. And that's basically the endpoint that you will connect to. Cool. So here's how you add an environment variable to your debug properties. You click the little debug menu at the top of Visual Studio, and you click build a bot properties, or build a bot will be replaced with whatever your project name is. Then you scroll down a little bit, and you'll see a section for environment variables. You enter token, and then you put in a UUID. There is a link at the bottom there if you want to generate a new UUID. You basically just open that website, and you can just click copy, and you just paste it in there. Cool. Next up, we initialize our connection with a builder. Builders are commonly used in Java and .NET, but I think pretty much every language that has a single R client uses that builder pattern. So if you are very used to Python or C++ and you see the builder pattern, it's a little bit jarring. We don't need to worry about logging. You can configure it if you want. You can leave it out. This can just be helpful for when debugging. Then we enable automatic reconnect, which is helpful, especially when testing locally for flaky connections, for example, if it pauses on a breakpoint in your debugger for a couple seconds. And then finally, we start the connection and we wait for it. Our main function isn't asynchronous, so we just do .wait to wait for it to finish, and then we simply print out connected to the runner. Then once we run that, we end up with this, connected to runner, and it immediately exits. We will fix that later on, so don't worry. Cool. Now is your chance to catch up if you need. If you want to see a specific side, don't hesitate. Just stick your hand up. I'm happy to move back and forth. And other than that, you can ask our helpers for questions. You can ask me if you have a question. Cool. So let's carry on with our next step now. So first, we're going to talk about DTOs, which are data transfer objects. These are basically objects that are used by Signal R to communicate payloads when sending events back and forth. In our case, in our models folder, if you haven't created that, you can just create it. We create a bot state DTO. This basically represents the different fields and sort of the state of the bot as far as the runner hub sees it. So they have basic things like your level, your state, your position, and we will go into more detail in this in a little bit. And the getters and setters, at least in .NET, are quite important because Signal R uses them to actually build the model when it receives the event. Then we have an input command enum. These are basically all the available options you have to send to the runner to tell your bot to move. So the basic left, right moves left and right, obviously. Up will either jump or climb if you're on a ladder. Up right and up left will jump diagonally. And then down will either go down a ladder, or if you're on a platform, it'll drop you through the platform. And then digging will basically do the same movements, but it'll dig through ground. So these values, you can find them in the game engine repository. If you haven't yet, I would recommend checking it out. If you are planning on running it locally, you will need to go through it at some point. Feel free to poke around in the source code. You can even submit pull requests if you have bug fixes or improvements. We don't guarantee we'll merge them, but we will look at them and consider them. Then we have a bot command. So when you send your input command to the game engine, you need to send your bot ID as well. We'll handle getting your bot ID in a little bit, but then we basically wrap it in this class along with your bot ID and the action and send that off to the game engine. So then in our bot state, we simply just create a toString method. This is not necessary. This is just helpful. If we are running it in our terminal, it'll print out the state and we can see it, and it can help us make decisions about how to improve our bot. At the beginning, it basically just prints out a bunch of kind of metadata. So our current level, our current state, etc. And then it prints out the hero window as a big block of text. Note that for the hero window, we print it out. We start with the Y coordinate and do it in reverse because we're printing it row by row and not column by column. So just bear that in mind. You will need to flip it or else you end up with a rotated or upside down view. So now in our program.cs, we at the top add a new variable for our bot ID. We also, after starting the connection, we add a listener for the registered event. When we get that, we receive the ID from it, and we print it out to the screen, and we save it into our variable. Next up, we send the register command, and we give it our token that we got from step 1, and we give it our nickname as well. Then, as you saw in the previous section, when we run the bot, it basically just connects and then immediately exits. So we fix that now at the bottom of our main function by basically just sleeping for 300 milliseconds and just checking as long as we are either connected or reconnecting, just as long as we haven't disconnected. Now we finally do some movement. We basically listen for the receive bot state event from the runner hub, and we print the bot state to the screen, and then we basically just send back move right. So for now, pretty much all we do is just keep moving to the right. And as you can see, after about 4 ticks or so, the position starts to update as we start to move. And we also get our ID back from the server. Cool. Sorry, that was a bit quick. We are like a little bit pressed for time. So I'm going to go through the slides quickly, and then afterwards in our breaks, you can feel free to ask questions and look at the repo if you get stuck. Cool. Let's see, where are we? Okay, so now we're quickly just going to talk about how to interpret the state, what all the different values mean. So firstly, X and Y is basically just your position. It's just an X and a Y coordinate, nothing much to it. Then the elapsed time and game tick are basically just representations of how long the game engine has been running. Tick is obviously just the number of ticks that has passed, and elapsed time is in real time how much time has passed since the beginning of the game. The connection ID you really don't need to worry about. That's like an internal signal R thing, and mostly it's just used by the engine itself to kind of work out which bot is which. Then the current state is just a string representing what the engine thinks your bot is currently doing. So it'll say idle if you're just sitting still. It'll say falling if you're falling, jumping, etc. Then the current level is which game level you are on, because we have 4 levels. You collect all the collectibles and then progress to the next level and so on. It starts at 0. So 0 is the first level and it ends at 3. Then collected is how many collectibles you have. Note that this is the current level. So when you advance to the next level, it resets back to 0. Then the hero window, which we will discuss in more detail in the next slide, is basically like the eyes of your bot. If a bunch of you have been managing to run it successfully, and that's good. If that big block of text that gets printed out with all the 0s and 1s and 5s and whatever, that's your hero window. Then radar data basically just tells you information about other players around you and where they are and how to reach them. But for our bot, we're just going to ignore that for now. We're basically just going to find some collectibles. But the radar data will be helpful if you want to take a more aggressive approach. So the hero window is basically the bot's eyes. It's a 2D jagged array of tiles, as opposed to C#'s fancy 2D arrays. But you can always trust that the dimensions will be the same, so you don't have to worry about checking the length of each row. If that doesn't hold true, please file a bug report and tell us. That shouldn't be the case. And each type is represented by, or each tile is an integer that represents the type. You can find all those details in the object type enum in the engine source code, but I do list it here later. And then the middle 4 tiles are your bot, so it's 2 by 2. You'll notice that the hero window is an even number by an even number, so those center 4 tiles will represent your bot. So now I'll quickly discuss the basic architecture for the bot. We just have the program file, which is the main class. That's what most of us have been working with now. We haven't gone to any of the others yet. So we have our bot service, our state machine, and then for now, we just implement 2 states. We have searching and collecting. What will happen is we'll search for a collectible, and once we find one and find out how to reach it, we go to the collecting state. Once we collect it or miss it, we go back to searching. So the program is basically just responsible for reading our configuration, setting up the signal R connection, registering our bot, as that's as far as we've gotten so far, as well as the message listeners for receive bot state and registered, and then also the application lifecycle. For now, that's basically just the loop. You can also do fancy things if you disconnect or whatever. Then in our bot service class, we are going to store the bot information. For us, the only thing we care about is the bot ID. And it also houses the brain. So this is where the state machine will live. And it's responsible for basically taking the state from the runner hub and handing it off to the state machine to figure out what to do with it. It then gets an input command back from the state machine and wraps it in a bot command along with the bot ID. So now the state machine is the brains of the bot. This is where all the exciting stuff happens. It has one active state at a time, as we discussed in the theory. And basically, it doesn't do much on its own aside for allowing states to transition between each other. So it has a function for them to do that. And it basically just hands off the bot state to the currently active state and gets a command back from that. So now we'll get to some code. We've got our bot service. It basically just has a variable for the bot ID as well as a setter to set it. Currently, it lives in the services folder, and it has a process state function. For now, we basically just move our return right to here. And then when we get to the state machine, we will add that. We'll add it here and pass the state along. Then we make some changes to our program.cs file. We, rather than having a variable for the bot ID there, we call the setter on the bot service. I forgot to show it in the slides here, but you do need to add the bot service. You initialize a new variable in the program file. And then when we receive our bot state, we basically just get the bot command back, check if it's null. If it's not null, we send the command over to the server. The reason we check if it's not null first is because we don't necessarily always want to be moving. You could definitely do that, but in our implementation, while it's busy changing states, rather than do some kind of fancy checking to see if it's changing, we basically just sit still while we're waiting to change. Cool. Now we'll have another quick break to catch up if you guys need, and feel free to ask any questions. So don't worry if you get stuck. And if your code doesn't work the first time, don't worry. I had to debug it for many hours when writing it the first time. So that's just how it goes. But you are welcome to ask questions afterwards. And I think we'll still be here around for like a while afterwards. So we start with the state machine, which basically just has a current state variable, which we initialize to the searching state when we start it. And it also exposes a change state method that the individual states will use when they want to transition to other states. We also give it an input command process state function. And this will basically just call the same function on the current state. So essentially, all the state machine really is at this point is just a housing for states to live in and to transition between each other. Then we have an abstract class for our states. All our individual states will inherit from this. We are using C#, so we are using object-oriented programming. I'm sure that is a controversial opinion, but it's what we have. So it also has a reference to the state machine. This is just so that it can call that change state method on the state machine. And it also has an abstract function for process state. So the responsibility is on each individual state to implement that. So we start off with the barebone structure of our searching state. We basically just override the constructor and call the superconstructor with our state machine. And for now, once again, we just return right. Don't worry, we will get to some actual movement. And then in our bot service, we initialize a new state machine at the top of our class. And we change our process state function to now speak to our state machine. So that might return null. If it does, we return null. Otherwise, we return a new bot command, same as we were doing before. Next, we have like a couple helpers. This is that object type enum I mentioned earlier. You can find it's basically exactly the same in the source code for the engine. The values are quite important. So we just need to make sure that it matches up with that. Otherwise, you'll think you're on a platform when you're on a hazard. Then we basically create a point. The reason we did this is because there's not a very nice default kind of built-in point or vector, at least not that I could see in C#. I'm sure JP is screaming at me right now. We also define an equals method because we basically want to check equality based on the X and Y coordinates, not based on the kind of reference to the individual variable we have. Then we simply have a bounding box. This basically just represents a rectangle. For now, we only really use it for our player, but you are welcome to use it to see the whole area that a platform takes up, for example. It basically just has a position, an X and Y, that will refer to the bottom left corner, and then a width and a height. And then it has some helper functions, one just to get the position, and one to get the size, as well as to get the Y coordinate of the top and the bottom, and the X coordinates of the left and the right. Those are not necessary, they're just helpful to make our code a little bit clearer when we write it out. So next up, we have a function in our searching state that basically just gets the bounding box of the player. We could kind of do hero window.length divided by 2 minus 1, every time we need to get it, but this just makes it a bit more concise and a lot easier to use. Then we add a helper function that will basically tell us if we are standing on a platform. It basically just looks at all the blocks underneath us and checks if any of them are a platform. We then have a similar one, but just for if we're on solid ground. Then we add a function to check if we can climb. We basically define this by checking if any of our points within our bot is intersecting with a ladder. Then we add a check to see if a hazard is in front of the player, because if there's a hazard, we want to jump over it. We don't want to just walk right over it. So we basically just check up to 2 blocks in front of the player, below the player, and if any of those are a hazard, we say, okay, cool, we've got a hazard in front of us. And then we do a similar thing for the wall, which basically just checks if there's blocks sort of sticking up over the ground. So you'll note there, instead of saying player bounds.bottom -1, I just did .bottom, because obviously there might be ground on the ground. So then we basically add a function to check if we should jump. For now, we basically just check if we are on the ground or on a platform, because if we're not, we won't be able to jump. And then if we are, we check if there's a hazard in front of us or if there's a wall in front of us. This should hopefully prevent our bot from getting stuck in walls and from running over a hazard and just resetting back to the beginning. Then we change our process state function. We basically check if we should jump. If we should, we return upright. We don't want to just jump on the same spot. And if we can climb, we just climb. Maybe not the smartest decision, but it does tend to lead to our bot kind of going up and to the right, so it kind of goes off in its own direction. Otherwise, we just return right and keep running. So now when we run this, we can see I ran it for 1,000 ticks and we collected 3. Nice, cool. But we can probably do a little bit better than that. So we start with a simple class to represent a path. This will be used by our pathfinding function. It's basically just a list of nodes. But when we add them, due to the way we construct our path, we insert them at the beginning, so it's kind of like a stack. The reason we do this is because when we construct a path, we give it our end goal and it works its way backwards. So we just want to make sure it's in the right order. Then we also just have a length, which basically just returns the length of the array. Then our node basically represents a point, but with some extra kind of helper functionality for our pathfinding algorithm. So we have a G cost, which is for generalized cost. That is basically just how far away our node is from our end goal. That is helpful in kind of prioritizing which points to check out. Then we have the H cost, which stands for heuristic cost. For us, we just use the Manhattan distance to determine as a heuristic. That's basically just a kind of rough estimate of how much or how many steps we'll need to take to reach the end. You have several options for that. You can either use as the crow flies, Pythagoras' theorem, anyone, or you can use just the length, or you can use just the height. It's up to you. Then the F cost is basically just the total cost. So it's basically just our G cost plus our H cost. And other than that, we add a operator to basically cast our node to a point. It'll essentially just return the X and Y coordinates as a point. It's not necessary, but it does help make things a little bit cleaner. And then we also add an equals function, because when we are comparing whether 2 points or whether 2 nodes are the same, we don't care about the individual costs. We just care about if they are in the same space. Then we add some functions. This is in, if I go back to that slide, I think I skipped over it a bit quickly. So now we're going to be looking at that pathfinding.cs file. That's basically just a class with a bunch of abstract functions to, sorry, not abstract, static functions to kind of help us do our algorithms and stuff. That's just the way I organized it. You are free to organize it however you want. I'm sure there are many better ways to do it. But go ahead. I think Zoom's taking a bit to catch up. Cool. So the first one we add is the Manhattan distance. If you don't know what the Manhattan distance is, it's basically just, instead of checking in a straight line, it's if you go only horizontal and only vertical. It's the distance you'll need to travel. Then we add a function to construct a path. So once we've found our end goal, we basically just walk through all the parents back until we get to the end of the path. Then we add a function to check if we can actually reach our path or our node, because it's pointless even considering a point if there's no way for us to get to it. You know, if it's like floating 3 meters in the air, there's not really much point. Basically, this just firstly checks if it's out of bounds, because otherwise we'll run into some nasty out of bounds errors. And then otherwise it checks if it's a hazard or if it's inside a solid. We say, no, we can't reach that. Otherwise, we basically just check a little bit below us if there is ground, up to basically our height above the ground. We could extend that to see whether we could reach it via jumping, but that is an exercise to the listener. Then we finally get to our A* algorithm. This one is quite complicated, so buckle up. We start with our start and our end points. We create nodes for them and set their parents to null. Then we calculate the heuristic for our starting node, and we create 2 new sets. One is for the open set and one is for the closed set. The open set is basically all the nodes that we are still going to process. And then the closed set is for nodes that we're done with. We have stopped processing them. We don't care about them anymore. So we start off with just adding the start node into our open set, and then we enter our while loop. The while loop is coming now, but if we exit the while loop without returning anything, we just return null. We didn't find a path, just leave it. It's not always guaranteed that you're going to find a path. Then in our while loop, we basically loop while we have items in our open set. So we basically take the first node off the top, and if it is our goal, yay, we found our path. We then construct the path and return it. Otherwise, we move the current node into the closed set. We're done with it now, and we continue. And we also remove it from the open set. So now we get all the neighboring nodes, and we loop through all of them. If we've already processed that node, we just ignore it and skip it on to the next one. So that's if it's in the closed set. And then we check if it is in the open set. And if it isn't, we put it in our open set and say, OK, we're going to process it later. Otherwise, if it is already in our open set, we check the current cost that we have for it now. So we basically how far we need to travel. And if it is shorter, so if it has a smaller cost than what we already have in our open set, cool, we found a better path. So we set the current one we have to use our new parent and our new cost, and then carry on. Then after this loop, we basically sort our open set by the total cost. We want to consider the sort of closest ones first. This is our neighbors function. We basically take all the 8 surrounding tiles and we check if we can reach them. We basically just don't consider them if we can't reach them. And also we make sure that we're not going out of bounds again. Then in our searching state, we add a new function to basically find all the collectibles that we can see in our hero window. It basically just loops through the whole 2D array and constructs a list when it finds a collectible. Then we add a search for collectibles function, which will basically, we first sort of get all the collectibles we can see with that function we just saw. And then if we can't see any, we exit. There's no paths to be found here. Otherwise, we sort our collectibles by Manhattan distance and we take the closest 3. You can take more, you can take less, you try all of them if you want, but I limited it to the closest 3 because we have 150 milliseconds in which to process and respond. So any more and we might risk taking too long to respond to the game engine. And if you're feeling fancy, you're welcome to use multi-threading to calculate them all in parallel. A couple of you have mentioned multi-threading. Well done. But for now, we just calculate it like that. Then we go through our 3 collectibles and we keep track of which one has the shortest path. And if we have successfully found a path, we change to our collecting state, which we'll go over next, and then we give it the path that we found. Then we add a call to our search function in the process state. And if we did find a path, we return null, because if we keep moving while handing over states or while changing states, we risk messing up the path that we found. Certainly, it's not optimal, but it works. It's quick and dirty for now. You are free to improve on it. Then in our collecting state, we basically have a variable for the path that we have found. And we have a point or a variable for whichever point we are currently on within that path. And we have an index, which is basically how far along the path we are. And then in our constructor, we set the index to 0, and we set our point to the next point. So we basically grab the next point off the path. So here's the next point function. It basically just returns the point at the current index and increments it. You will see, so the nodes function is an array of nodes, and we return a point here. That's where that fancy operator point thing comes in. Then we basically just have a function to calculate the direction that we need to move in based on our next point. Then in our process state function, we first check if we've reached the end of our path. If we are, we have either found our collectible or someone else grabbed it before us. So then we just go back to search for a new one. Then otherwise, we grab the next point and we calculate the direction we need to move to get to that next point. Then we just have a very ugly switch statement that basically just returns the relevant command based on our direction. And we can see here, I got very impatient. I only ran it for about 257 ticks, and we got 13, which is a lot more than our current 3. I'm sure if I ran it to all 1,000, it would have done a lot better, maybe even advanced a level, but patience is not a virtue I possess. And that's pretty much it. If you guys have been following along, and if you have managed to create a successful bot, congratulations, please pat yourself on the back.